The 6G reference project is a collaboration between 10 research and industry partners from 8 European countries. 6G reference involves the development of 6G hardware enablers for joint communications and sensing, including inbound MIMO full duplex transceiver innovations, addressing data capacity and scheduling challenges of distributed MIMO and monostatic radar sensing. Novel synchronization solutions addressing synchronization not only in frequency but also in phase and time. Full duplex synchronization scheme with simultaneous transmit and receive times for all access points to achieve super resolution. We also address novel RF and antenna components focused on reduced complexity and cost, including time-modulated arrays for simultaneous parallel multi-beam reception and transmission with low-complexity single RF chain hardware. Also, frequency-modulated arrays for simultaneous multi-node localization and sensing with super resolution in space. Antenna systems extending the capabilities of small arrays with reconfigurable intelligent surfaces while also integrating an environmental sensing element. Finally, dynamic filtering at the intermediate frequency and integrated in the antenna filtering state to provide high frequency selectivity to enhance the spectrum coexistence with other services, for example, with satellite communications in the 10 to 15 gigahertz range. This figure relates 6G reference hardware solutions to enable cell-free joint communications and sensing transmissions with system-level improvements and overall 6G goals. The hardware enablers described in previous slide can be found at the bottom of the figure. In particular, 6G reference addresses 4 main challenges. 1, the need for low cost and low power consumption. 2, accurate time and frequency synchronization between radio units enabling coherent transmissions. 3, the reuse of the same hardware for communications, sensing, and localization. And 4, the coexistence with other services in the 10 to 15 gigahertz range. The 10 to 15 gigahertz range is targeted since it not only provides new spectrum opportunities, but also efficiently balances the benefits and drawbacks of sub-6 gigahertz and millimeter wave solutions. The figure shows a simplified example of a distributed MIMO system with only one cabled 6G network node providing data and an accurate time and frequency reference. Radio units access points cooperate to realize over-the-air synchronization via full duplex synchronization in transmit and receive time signals in green and data distribution gathering in blue arrows. 6G reference will focus on the centimeter frequency range since it is seen as an important frequency range where new frequency spectrum can be available for 6G use cases that require outdoor and indoor mobility. This figure shows a generic and preliminary system-level vision that will be refined in the first stages of the project according to the outcomes of other projects working on 6G architecture. We addressed the design of the radio unit in a generic way that could fit multiple specific deployments. 3 different cases are exemplified in the figure. Case 1, radio units 1, 2, 3 near the center of the figure are directly connected through the front hall to the same central unit. This connection not only transports data, but also distributes the master frequency and timing reference to all radio units, denoted here as the golden reference. The assumption here is that in massive cell-free deployments, this front haul and synchronization link will not always rely on fiber, but also on wireless solutions. Case 2 is exemplified by radio units 4 and 5 to the right of the figure that do not have direct connection from the central unit, but are in fact cascaded to radio unit 1. Case 3 corresponds to radio units 2 and 6 at the bottom of the figure that coherently transmit to one user but are attached to different central unit, which may happen often in a densified cell-free deployment. In all these cases, The aim of synchronization mechanisms is to provide time alignment at the radio unit's array planes. Better time synchronization using full duplex synchronization can relax processing mechanisms due to potential time difference of arrival to the different users and can further enable coherent transmission for radar sensing. The 6G reference project involves the development of hardware concepts and show their feasibility in CMOS as 8 integrated circuits or chips. This figure describes the 6G reference technical life cycle. It will start with identification of a baseline 6G cell-free architecture and use cases, which will define the operating conditions of the technological enablers addressed in this project. Then system-level simulations of these enablers using the identified architecture will be performed with the aim of determining in depth the capabilities and technical specification of the different components to be designed. The resulting operational components from the tape-out will be experimentally characterized in order to extract parametrized models to be fitted again to system-level simulations. Such simulations will thus permit evaluating the system performance improvement provided by the developed 6G reference hardware solutions, considering the real capabilities and impairments introduced by them. In parallel, the individual developed components will be integrated in proof of concepts to experimentally validate them and assess the achievement of the project objectives. Now, this figure presents a simplified conceptual block diagram of the targeted radio unit design. The final architecture may deviate from this initial proposition, but it serves as a good starting point for radio unit design. The 8 integrated circuits are shown in green. In blue, filtering antenna and RIS. It also shows how the interference canceling in the red boxes is shared between the RF stage at the right-hand side of the figure to reduce the power level of the interference in the following stages. At the analog intermediate frequency stage, at the center of the figure, using a filter bank approach, it is possible to reduce the interference below the signal level. Finally, at the digital level, at the left-hand side of the figure, high interference canceling can be achieved by adopting complex algorithms. Antenna solutions include antenna-in-package designs provided for low coupling between transmit and receive elements for full duplex operation and integrated RF filtering, 3D printed waveguides for high efficiency operation, a reconfigurable RIS to expand the capabilities of these small arrays at an affordable cost, and the development of environmental sensing elements. One of the largest concerns in full duplex transmission is the transmitter's power and noise coupling back to the receiver.
Ignacio, you have 1 minute left, so please.
Right, and interfere with a much lower power received signal, which is called self-interference. Full duplex antennas arrays will be addressed, providing isolation between transmit and received elements. Finally, we will address time-modulated arrays and frequency-modulated arrays. At the left-hand side, you can see a time-modulated array. So each of these beams, if this array is time-modulated, will have an associated frequency to them, and this can be filtered out at the receiver with an intermediate frequency filter. And on the right-hand side, we can see a frequency modulated array where a fixed frequency offset between antenna elements is used. The time-varying array patterns break the conventional static phased array limits, allowing localization and radar sensing of multiple objects with super resolution. And this will conclude the talk.
Perfect. Thank you so much. Right on time. And thank you very much for this interesting presentation.